let's continue with what we were talking about, Lewis dot structures. All right, so let's try to draw a Lewis dot structure for C2H4. Of course, the formula tells us there's 2 C's and 4 H's. You might have a little bit of a hard time putting them together, but you can see how they're drawn there. The 2 C's are connected to each other, and then each C has 2 H's attached to it. To figure out the number of valence electrons, each carbon, it has 4 valence electrons. And there's 2 of them, so that's 8. And then each hydrogen has 1, so that's a total of 12. The first thing we do is put a pair of electrons between each atom, attach each of the hydrogen to 1 carbon, and then the 2 carbons together. And when we do that, we've used up 2, 4, 6, 8, 10 electrons. We have 12 electrons, and we've used up 10, so we have 2 more. All right, so if you look at the top picture, you can see we have 2 more electrons that we can give. Each carbon needs 2 electrons. So we're a little bit in trouble because you might say, well, give each one of them 1. Well, they don't have 8 then. They would each have 7. And remember that electrons like to stay in pairs. Well, you might say give 2 of them to one of the carbons. Well, then the other one is short. So the best thing that we can do is to give both of those electrons to both carbons, since they both need 2. And you can see on the bottom what we've done is drawn a second bond between the 2 carbons, and this is called a double bond. So sometimes if there's not enough electrons for everyone to get 8, we have to give a double bond or a multiple bond. So a multiple bond occurs when there's not enough electrons. A double bond is a sharing of 2 pairs of electrons, which is a total of 4 electrons. 2 pairs, 4 electrons. And a triple bond is a sharing of 3 pairs of electrons, or in other words, 6 electrons. Since multiple bonds occur between the same 2 atoms, all of the electrons end up between the atoms, and you can count them for both sides of the bond. All right, so here's just some other other examples. If you were to figure out NH3, N has 5 and each H has 1, so that's a total of 8 electrons. And if we bond the H's to the N, we use up 6. We have 2 more. Nitrogen needs 2 more, so we give those 2 to nitrogen. If you look at the next one over, CH3OH, notice that a carbon has 4, oxygen has 6, so that's a total of 10, plus 4 more is 14. If we make those bonds, the 3 bonds to the carbon from the hydrogen, we use up 6, and then the carbon to the oxygen is 8, the oxygen to the hydrogen is 10. Now we have 4 more electrons that have to go to the oxygen because it's short 4 electrons. The one on the top right, the 2 carbons make a triple bond. That means there's 6 electrons shared between the 2 carbons, and then 2 electrons shared with each of the hydrogen. Each carbon shares with a hydrogen. If you figure out the valence electrons, each carbon has 4 for 8, plus 2 more is 10, so we need to figure out how to give all the elements 8 electrons with only 10 electrons, and this is how you can do it. The 2 oxygen, O2, again, O2 has 12 electrons. If you tried to give 8 to one of them, if you just drew a single bond between the oxygens and gave one oxygen 6 more, the other one would be short. So again, we don't have enough electrons, so we have to make a double bond. But what I want you to be able to do is to look at a structure and understand how many electrons an element has, the difference between a shared pair and an unshared pair, and basically that's it. Okay, one more twist on the covalent bond. We talked a lot about polyatomic ions back in Unit 5. And all I said then was that it was a group of atoms that together have lost or gained electrons. Well, it's exactly what it is. A polyatomic ion is actually a group of atoms that have been covalently bonded together, but by themselves they would not be able to form a compound without adding or subtracting electrons. So everything you do, everything the same way. The Lewis structure can be drawn for polyatomic ions. We use all the same steps except for one change. When you're trying to figure out how many valence electrons there are, we have to, or at least if you want to figure out how many electrons are available to make the structure, you figure out the valence electrons just like before, but you need to add one electron for every negative charge. Or if it's a positive charge, you subtract one electron from the total for every positive charge. Now, it seems a little bit counterintuitive, but don't forget that electrons are negative. And so if you have a negative charge, it means you have extra electrons, so you need to add that number to the sum of the number of electrons. So some examples. NO3 negative. Well, N comes in column 5. Each oxygen is in column 6, so that's 18, 19, 20, 22, 23 electrons. But because of the negative charge, we have to add one more, so there's a total of 24 electrons. Remember, I said earlier that you really need to have an even number of electrons, and so this is basically what's happening. Now, NH4 positive, the N is 5 again. Each hydrogen is 4, so that would give us a total of 9 electrons. If one electron is removed, we take away one. That means we have 8 valence electrons. So polyatomics are basically just the same, except we have to adjust the number of electrons. So let's do an example. Let's draw a Lewis dot structure for SO3 negative 2. Again, we have one S and 3 O's. They're going to be organized like this. It might be a hard one to figure out, but I'll just tell you the S goes in the middle. Now, sulfur and oxygen both have 6 valence electrons, so we have a total of 24 electrons from the S and 3 O's. But there are 2 more electrons because of the negative 2 charge, so that means we have a total of 26 valence electrons. So if we start by bonding the S to the 3 O's, we've used up 6 out of the 26 electrons, so we have 20 left. If we then give each oxygen 6 more so that they have a total of 8, we've used up 18 more, and so we still have 2 electrons left. Well, if you look at the sulfur needs 2 more, and so we can give those last 2 electrons to sulfur. You can see on the top structure. So SO3 negative 2 doesn't have any double bonds or any kind of multiple bonds. Every element has 8 electrons. Now, just a little note, if you see on the bottom, if the SO3 didn't have the negative 2 charge, then we wouldn't have those extra 2 electrons. There would only be a total of 24 electrons. And going back to the previous page, before we added those two electrons to sulfur, we would be stuck. We would have given up all of our electrons, and we would still need 2 more to give sulfur. Well, in that case, remember that if you don't have enough electrons, you have to make a double bond. So in fact, the Lewis dot structure for SO3 without the negative 2 charge looks like the structure on the bottom, where there's a double bond between one of the S's and one of the O's. All right, so hopefully now you'll be able to look at a Lewis dot structure and understand what the different dashes and dots mean. However, Lewis dot structures are only 2-dimensional. They can't really show us exactly what the molecule looks like. So what we need to do is to predict the shape of the molecule. Remember that molecules are 3-dimensional structures, and so a flat 2-dimensional drawing won't really tell us what we should be able to see. So what we're going to do is predict the shape of the molecules by using what's called the VSEPR theory. VSEPR stands for valence shell electron pair repulsion theory. So what all those words mean? Well, valence shell, you know that the valence shell is the highest energy shell. Electrons that are in the valence shell. Pair, because we know that electrons like to stay in pairs, repulse each other. So because electrons are negative, and now they can stay in pairs, they have their way of sort of hiding each other if if their spins are different. We talked about that back in Unit 4. But other than that, electrons are negative and they're going to repel each other. So they're going to try to stay as far apart from each other as possible when arranging themselves around an atom. Since they repel each other, they don't want to be close to each other, and so they organize themselves in particular shapes, depending on how many electron clouds there are. Electron clouds, regions where electrons are concentrated. So, if we apply the VSEPR theory to the electrons pairs of a central atom, we can predict what the shape of that molecule will be. Okay, so this is what we're going to do. Look at the Lewis structure, identify the element whose geometry is of interest. Usually that's the center, but we've seen a few elements where there's more than one in the center, so we'll have to decide. We'll have to look at each of them individually, but generally the central atom. Then what we need to do is count the number of electron clouds surrounding the atom. Now, how do we count the number of electron clouds? Well, any bond of any kind counts as one electron cloud. But also, the unshared pairs count as an electron cloud. That's very important. We tend to forget about the unshared pairs, but they're actually very important because they take up space. There are electrons there, and you can't ignore them. So, we're going to count any kind of bonding electrons as one region, and then any unshared pairs as one region. Now, because double and triple bond electrons are all concentrated in one spot, we're going to count any kind of bond as one electron cloud. So whether it's a single, double, or triple bond, count that as one region of electrons or one electron cloud. Then, once you figure out how many electron clouds you have, you can predict the shape by what we're going to see on the next few slides. All right, so if there's two electron cloud regions, in order to get as far away from each other as possible, they are going to line up in a linear shape. If you can picture electron clouds like a balloon taking up space, and that's sort of my trying to draw it there on the right hand side. If you hold two balloons at the center, they're naturally going to fall apart from each other in a line. So the angle between the x and the other x is 180 degrees, because we're going all the way across to the other side, 180 degrees. And so the molecule, which you see a sort of a shape of on the bottom, looks like a line because all the atoms are in a single line. Okay, so the linear shape is if there are two electron cloud regions. If you have three electron cloud regions, so try to hold three balloons together at the center, they're naturally going to arrange themselves in a flat triangle. And we call this triangular planar. You do need to use both words. It's a triangular, and it's also planar, meaning that it's a flat molecule. It's all in one plane. So, if you look at the right-hand side, the molecule with the white and pink, you can see that there are three things attached to the center, and they're as far apart from each other as possible, and there's nothing above or below the plane of the molecule, so it's planar. The bond angles between each of the atoms around the center are 120 degrees, because now it's a triangle, 120 degrees. All right, if there are 4 pairs, now we're starting to get into some 3 dimensions. 4 pairs will be located at the 4 corners of a pyramid-like shape called a tetrahedron. So you can either use the word tetrahedron or tetrahedral shape. That molecule's tetrahedral, or it is a tetrahedron. Tetrahedron is the noun, tetrahedral is the adjective. So if you look at the picture on the left, it's a little bit different. I couldn't draw my balloons in 3 dimensions, but if you have 4 balloons held at the center, they're naturally going to form this sort of pyramidal shape that you see here. If you look at the center molecule with the A's and the X's, if you see the wedge, the sort of the triangular bond, that means it's sticking out toward you, and the dashed line means that bond is going away from you. So we're trying to draw 3 dimensions in a 2-dimensional paper. Okay, so the bond between the X's is 109.5 degrees. And so on the farthest right, you can see a molecule that has 4 things attached to a central atom, has this tetrahedral shape. Now, there are structures for 5 and 6 electron clouds, but we're not going to cover them in the course. They get even more complicated 3-dimensionally, but we're just going to stick with 2, 3, or 4 because those are kind of our standard molecules. All right, so let's look at some examples. If we look at CO2, we want to, first of all, find the element of interest. That's always the one in the center. So we're looking at the carbon. So we only want to look at electrons directly attached to the carbon. Count the number of electron clouds. Well, there's a double bond on the right, that's 1 cloud, and there's a double bond on the left, that's another cloud. Now we don't count any of the dots because they're only attached to the oxygen. So we're only looking at the central atom and what shape it is. So there are 2 double bonds. Since we count a double bond as 1 electron cloud, there's a total of 2 electron clouds attached to that carbon. This means that CO2 is a linear molecule, and the bond angle is 180 degrees. So that picture down at the bottom is actually what a CO2 molecule looks like. The C and then each O coming out from either side of the C in a linear fashion. All right, if we look at the Lewis dot structure for NH3, again, first find the element of interest. In this case, it's going to be the N. The N is in the center. And we want to count the number of electron clouds attached directly to that N. Well, as you can see, there's 3 bonds. There's an N attached to an H, and another H, and another H. So that's 3 electron clouds, 3 bonds. And then we also have to count the unshared pair. So there's 1 unshared pair at the bottom of the nitrogen. We have to count it. So that gives us a total of 4 electron cloud regions. Okay, so 4 means tetrahedral shape. So the tetrahedral shape, and if you look sort of down at the bottom hand left where I've drawn the N, and then I've gone back to the previous page where I had the A and the X's. I've drawn the N in the center, and then the 3 coming down are hydrogens in the plane of the paper. The other hydrogen that's got sort of the wedge is coming out toward me, and then the one that's got the dashed line is going back away from me. And then the 4th spot out of the 4 spots, the 4th spot holds the unshared pair of electrons, which, like I said, you have to have room for them. They take up space and you can't forget about them. So in fact, this molecule has the overall tetrahedral shape. And then if you look at the molecule on the right, the blue and white, actually if you kind of cover up the 2 dots, which of course they're there, they take up space, but if you actually look at just the atoms in the molecule, you can call this the pyramidal shape. Sometimes it's called triangular pyramidal shape because it looks like a little pyramid. So the main thing I'm looking for is tetrahedral, and then if one of the 4 regions is an unshared pair, we can call that pyramidal. All right, let's look at the shape of CH2O. Well, again, what's the atom of interest, it's the carbon. The carbon is in the center. So if we look and see what's attached directly to that carbon, there's a bond to the H, a bond to another H, and a bond to the O. Don't forget that the double bond only counts as one region because it's all between the same two elements. So in this structure, there are 3 regions of electrons, or 3 electron clouds, and this takes the shape of a triangular planar. So in fact, those hydrogen need to be, that Lewis dot structure in the top right is just a 2-dimensional picture of it, and in fact, the structure down at the bottom on the left with the C, double bond O, and then the 2 H's coming out, making a triangle shape, is more what the molecule looks like. And then if you look at the right-hand side, that's the actual molecule with a carbon in the center attached to 2 H's and attached to an O. So it looks like a little triangle. All right, so keeping this in mind, predict the shape of H2O. And if you don't remember anything about this class in the future, I hope that you'll at least remember the shape of water. It's really important. So we look at it. What is the central atom? It's an O. So how many regions of electrons are attached to the O? There are 4 regions. So there are 2 bonds to each hydrogen, and there are 2 unshared pairs. So we have to count all 4 of those. That gives us the tetrahedral shape. And if you look at the bottom left-hand structure, you can see that I've got the tetrahedral shape, and I've got an atom attached to the 2 bottom ones, and then the unshared pairs attached to the top one, and then the bottom one going to the left. So that's exactly what the molecule looks like. The center is attached to 2 atoms and is attached to 2 unshared pairs. Sometimes you'll see the water molecule drawn as it is in the bottom right-hand corner. It's a bent shape. So, and sometimes you'll see the molecule looks like the one just above it with the red ball and the 2 white balls. It's got the bent shape. If you look over to the left, you see the tetrahedral shape, and if you rotate it around, you can see that it's got that sort of same bent shape. And often when you're drawing the molecule, you don't have to draw the unshared pairs in, but you do need to know that they're there because they do give the overall shape to the molecule. So again, sometimes this shape is called bent. Now, if I said, what is the shape of this molecule, your first answer should be tetrahedral, but it is also, if 2 of the 4 are unshared pairs, then we call that bent. And in fact, you can see that the molecule looks bent. So this chart will give you a little bit of a summary. So if you have 2 electron clouds and both of them are bonded, then we have the linear shape with 180-degree bonds. And an example is CO2. If we have 3 electron clouds, we have the triangular planar shape. Now, if all 3 of them are bonded, we get the top one, 120-degree angles, which the example is CH2O. If we have 2 of them bonded and 1 unbonded, or 1 unshare, we still have the triangular planar, but sometimes we call this the bent shape. And SO2 is an example of that molecule. Now, the third possibility is to have 4 electron clouds. And again, now you can see if you have 4 electron clouds and all 4 are bonded, we call that tetrahedral. Example of that is CH4. If you have 4 electron clouds where 3 are bonded and only 1 is unshared, then we call that pyramidal, tetrahedral pyramidal or pyramidal. And you can see NH3 is an example of that. And then finally, if you have 4 electron clouds where 2 are bonded and 2 are unshared, we call that tetrahedral bent. And that is what water is. So this is a nice chart that you can go back and reference. Just a little note on representing molecules. So there are different ways of representing the same molecule. A formula just gives the ratio, H2O. The Lewis structure gives a 2-dimensional picture, and so usually we put the unshared pairs and the bonds in there, but they don't really give any indication of the shape. The ball and stick model, which we've seen throughout this lecture, has the molecules bonded to each other with a little stick in between. It gives a three-dimensional shape. But sometimes we also will see the space-filling model, which is actually a more realistic picture of what the molecule looks like. All right, now, most molecules, of course, are large and they have lots of bonds. And so sometimes, I'm not going to get anything real complicated, but sometimes you'll have a molecule that has more than one center atom. It's not possible to determine the overall shape of a huge molecule. What we want to do, if I gave you one of these molecules down here and I said, what is the shape? You would actually have to look at each possible center and say what that structure would be. So if you look at the molecule to the left, find one that's in the center. Well, there's a carbon that's in the center. Actually, both carbons are centers. So if we just look first at the carbon on the left and see what is bonded directly to only the carbon on the left. Well, you can see there's 3 bonds to H's and 1 bond to a C. So altogether, that's 4 regions. 4 regions is tetrahedral. So the carbon on the left-hand side would be a tetrahedral shape. Now, if we look at the carbon on the right-hand side, again, the same thing. It's bonded to 3 hydrogens and 1 carbon, which is also tetrahedral. So this is just 2 tetrahedral molecules stuck together to make one big molecule, but each carbon is a tetrahedral shape. If you look at the one on the right, very similar. Look at the carbon on the left of that structure. The carbon is bonded to 3 hydrogen and another carbon. So again, just like before, that's tetrahedral. But now look at the carbon on the right. The carbon in the right is also a center. It's bonded to more than one thing. But how many bonds does it have? Well, it has a single bond to a carbon, it has a single bond to an oxygen, and it has a double bond to an oxygen. Remember that the double bond to the oxygen counts as 1 region or 1 electron cloud. So the carbon on the right-hand side is bonded to 3 regions, which is the triangular planar. So the carbon on the right is triangular planar, the carbon on the left is tetrahedral, and we can just stick them together. There is one other center on this molecule, and that's the oxygen, because the oxygen is bonded to more than one thing. You can always find a center if it's bonded to more than one thing. If it's only bonded to one thing, then it's not in the center. So if we look at the oxygen, we know that it's bonded to a carbon, it's bonded to a hydrogen, so those are 2 bonds, 2 regions, and then it has 2 unshared pairs for a total of 4 regions. 4 regions with 2 bonding and 2 unshared. The overall structure is tetrahedral, but then we also can call it bent. So that's what you need to, if you see a bigger molecule, you have to look through each center and determine what its shape is. You can't get an overall shape for a molecule. And so one more example, what is the shape of C2H4? Well, if we look at the Lewis dot structure, which is there on the right, each carbon is bonded to a hydrogen, 2 hydrogen, and then it's double bonded to another carbon. So if you look at the carbon on the right, it's got 3 regions. 1 H, another H, and a double bond to the C. The one on the left is also a triangular planar shape. Well, if we stick 2 triangular planars together, you can look on the bottom. We've got the sort of looks like a little butterfly. The one carbon is a triangle, and the other carbon is a triangle, and they're stuck together, and so we have 2 triangular planars stuck together. All right, and this is very similar to the one I did before. What's the shape of acid aldehyde, which is that Lewis structure on the right, top right? Well, again, the carbon on the left has 4 bonds. It's bonded to 3 hydrogen and one carbon. So that's 4 regions, which is tetrahedral. So the carbon on the left is tetrahedral. The carbon on the right is triangular planar. And that is because it's bonded to 3 things. It's bonded to a carbon, it's bonded to a hydrogen, and it's bonded to an oxygen. So 3 bonds, which is triangular planar. And so you can see the structure below it in the molecular form, or you can also see where I've tried to draw it in the 3-dimensional shape. All right, so we've got one more slideshow to look at, which will tie together a lot of these things that we've been talking about.